All right, hello and welcome. Today, we're going to crack open the secret operating system of the entire universe. It's called quantum mechanics, and it's basically the set of rules that governs how everything, and I mean everything, works at the tiniest, most fundamental levels. So, let's just start with a big, kind of weird question. What if the solid, predictable world you see all around you isn't the whole story? We're about to take a little trip into a realm that completely defies common sense. But, and this is the key, it's a realm that makes our entire modern world possible. Okay, let's dive right in. In our everyday world, things are pretty predictable. You throw a baseball, you know roughly where it's going to land. But down in the quantum world, it's a whole different ball game. It's a world built not on solid facts, but on possibilities, on probabilities. So to get a handle on this world, we have to get familiar with its bizarre rules. But as strange as they are, these are the essential principles that dictate how reality itself actually works, at its very core. Okay, first rule up, wave-particle duality. This basically means that a tiny little thing, like an electron, can act like a solid little ball in a specific spot. But it can also act like a spread-out wave, almost like a ripple in a pond, existing in many places at once. The famous double-slit experiment proved this. Get this, even when they fired electrons one at a time, they still created a wave pattern on the other side. It's like each electron somehow went through both slits at the same time. And that idea leads to one of the most famous and strangest concepts in all of physics, summed up perfectly by the thought experiment of Schrödinger's cat. The core idea is that something can exist in a weird mix of states, like being both dead and alive, right up until the moment we actually look. The official name for this is superposition. A great way to think about it is like a spinning coin. While it's spinning in the air, is it heads or tails? Well, it's neither. It's a blend of both possibilities. It's only when we measure it, catch it and slap it on our wrist, that it's forced to pick a side. The very act of looking forces a choice. And it turns out, this quantum fuzziness isn't a bug, it's a feature of the universe. This is the uncertainty principle. What it means is there's a fundamental trade-off. The more you know about where a particle is, the less you can possibly know about where it's going. And it's not because our tools aren't good enough, it's a hard-coded limit of nature itself. And if you think that's strange, hold on. We've got a phenomenon that even Albert Einstein found so deeply unsettling that he called it spooky action at a distance. He was, of course, talking about our next rule. That spooky action is quantum entanglement. Imagine you can link two particles so their fates are forever tied together. If you measure a property of one of them right here, you instantly know the state of its partner, even if that partner is on the other side of the galaxy. That connection is instantaneous. It's faster than light. Yeah, just let that sink in for a minute. So, how does the universe even keep track of all this probability? It uses something called the wave function. You can think of it as a mathematical cloud of all the possibilities. So when we're not looking, a particle exists in this smear of potential. But the moment we measure it, the moment we look, bam, that whole wave of maybe collapses into a single definite is. Now, I know what you might be thinking. This is all just bizarre abstract theory that doesn't really matter, right? Well, this is where it gets truly amazing. This quantum weirdness isn't just trapped in a lab. It's in your pocket. It is the engine of our modern world. And that's not an exaggeration at all. Without our understanding of quantum mechanics, the entire technological revolution of the last 70 years, it just wouldn't have happened. The bizarre rules we just talked about are the absolute foundation for the devices we all use every single day. Just think about your smartphone. Its incredible power comes from billions of tiny little switches called transistors. And the only reason we can design and build those transistors is because quantum mechanics tells us exactly how electrons behave in materials like silicon. Seriously, no quantum mechanics, no computer chip. It is that direct. And what about lasers? That perfect, focused beam of light works because electrons inside atoms can only exist at very specific, separate energy levels. That's a core quantum idea. And that one principle powers everything from delicate eye surgery and industrial cutting to the fiber optic cables that bring you the internet. Even in the hospital, quantum mechanics is a literal lifesaver. MRI machines work because of a purely quantum property of atoms called spin. You can think of it like each atom having a tiny magnet inside. By tweaking those tiny magnets with radio waves, doctors get these incredibly detailed images of our organs and tissues, all without ever making a single cut. But here's the kicker. As incredible as all of that is, we are just scratching the surface. We're only at the very beginning of really harnessing the power of the quantum world. I mean, the first revolution gave us computers and lasers. The next one, well, it promises to be even bigger. The future really is quantum. We're on the verge of building quantum computers that can solve problems that are literally impossible for today's best supercomputers. We're developing quantum communication networks that are, by the laws of physics, completely unhackable. We're even looking at quantum effects to totally revolutionize how we get our energy. To put it all in perspective, it's like we're back in the early days of electricity. We've just invented the light bulb, which is amazing, right? But we can't even begin to imagine something like the internet or a global power grid. That's where we are right now with quantum technology. We're at the dawn of a new age. So that leaves us with this final, really fascinating question. We're at the very start of our quantum journey. We've built the first simple quantum devices. But what's that truly world-changing application going to be? What's our quantum light bulb? The one thing that right now we can't even begin to imagine.